Okay, Assalamualaikum and good afternoon. Going to start soon. Now lah, start now lah. Okay, because today is just 1 hour, so we're going to continue on heat integration. So last week we learned on what? Can you first of all can you hear my voice? Right. Okay. So if you can hear my voice, then we can proceed. Right. So last week we learned on what composite curve and problem table algorithm, right? So what is the significance of both problem table algorithm and composite curve? Anyone? What's the significance? What's the importance of this problem table algorithm and composite curve? It provides you the value of what? Anyone? What is the value that we can get from problem table algorithm? You have done this in the exercise, right? We get what? The value of minimum value of heat requirement QH and the minimum value of cooling requirement QC min, because we want to minimize the usage of any external energy from our from hot and cold utilities. Instead, we want to what? We want to maximize the energy recovery. We want to uh, recover as much as possible the heat from the process. So that's the importance of composite curve and problem table algorithm. Okay, right. Today we're going to look at how to design the heat exchanger network. Okay. Once we know what are the minimum requirement of hot utility and cold utility, then we can directly design our heat exchanger because heat exchanger here is we want to exchange the heat between the process streams from hot to cold utility, right? Boleh dengar ke ni? Macam tak ada response pun. Dengar tak? Tak ada suara pun. Nah, okay. Alright, so today we're going to look on how we can design the heat exchanger network lah. Okay, so you learn on what? From the composite curve and problem table algorithm, you also get the value of what? The pinch temperature for T pinch hot and T pinch cold, right? Alright, so the pinch set the absolute limit for process heat recovery. What's the meaning of this statement? Okay, you in pinch you have your T pinch, right? So as you increase the delta min delta T min lah, delta T min from pinch tu, we get the difference between hot and cold punya stream, the minimum permissible heat transfer temperature, right? So from there we get the value of T min. Sekejap. Kenapa tak boleh pen ni? Apa tak boleh ambil pen ni? Alamak. Okay, never mind. So from this is what? This is composite curve. So from composite curve, you can also get the value of T delta T min. So delta T min, so as you increase the value of delta T min, basically you will reduce the energy recovery from this two stream, hot and cold utility, but you will increase the energy requirement from the external utilities. But if you reduce the value of delta T min, what happened? You will increase the energy recovery from these two stream, hot and cold. But and you will also can minimize the external utility that you need to that you need that you can also reduce the energy external and I mean the value of external utilities lah, the delta H from hot, from heater, and cold utilities lah. For example, cooling water, right? So that's the importance of delta T mean value lah, right? Next, okay. You and from the previous class, you also know that delta T mean, okay, for a practical delta T mean, the value of T hot pinch should not equivalent to the value of uh, temperature of cold pinch temperature of cold stream lah, right? So T hot pinch must be not equal to T cold pinch, okay? Right. Okay, so from the pinch value, okay, so pinch will divide the problem into heat source and heat sink. So this is heat source and heat sink. So if you look here above the pinch, okay, this is above the pinch, and the left side is the area below the pinch. So okay, above the pinch, what happened above the pinch? The process acts like a heat sink where it receives a heat from the hot utilities, right? But what happened at the at below pinch here? What happened? The process acts like heat source where the heat from the process is what is reject to the cold utility. So basically, the pinch divide the problem into heat source and heat sink. So you know this is heat sink and this is heat source. Okay. All right. Okay. Let's say there is no heat transfer across the pinch here. Okay. Okay. In the area here, right? Your okay. The kejap. Yeah, this is okay. This process is in heat balance with QH min. While at this area, heat source, okay, the process is in heat balance with QC min, the cold utility, right? Okay, what if there is a transfer of heat from what? From from hot stream above the pinch to below the cold stream below the pinch. Is it possible? Yes or no? Yes, because the heat is transferred from hot temperature to cold temperature. Okay, what if there is a transfer of heat from the hot stream below the pinch to the cold stream above the pinch here? So you can see that the heat is transferred from what? From low temperature to high temperature, which means it is not feasible, right? So it is impossible to transfer heat from above the pinch to below, but uh, the transfer of heat from below the pinch to above the pinch is not feasible. Okay, now what happens if we transfer heat across the pinch in this direction from above the pinch to below the pinch? What happens? Okay, if we transfer a certain amount of heat, for example, XP unit of heat across the pinch, okay, both QH min and QC min will increase by the same value of SP. So this is the pinch equation. Actual equals target plus cross pinch. What is target here? Target is the value of QC min and the QH min lah, our targeted minimum energy from external utilities. So the transfer of heat from above to below pinch will result in the increase in the same unit or the same value of energy in QH min and QC min. So that's the effect of transferring heat across the pinch. All right. For a maximum energy recovery, okay, there must be no external heat, no external heating below the pinch. So this is the area below the pinch. Okay, okay, you must have no external. This is a external heating requirement. So in order to have or to achieve a maximum energy recovery, you must have no external heating below the pinch. Because why? Why? Because why? Because if you supply external heating below the pinch, okay, this will result in increase in the amount of the same energy in your QC min. That's why you cannot maximize the energy recovery lah if you have the external heating below the pinch. Okay, similarly, okay, for maximum energy recovery, there must be no external cooling above the pinch. So this is the area above the pinch. So this is the what? This is our external cooling. Okay. So if you supply external cooling utilities, okay, there must be an increase in the amount of um, hot uh, uh, hot utilities. Okay, with the same amount, for example here, SP lah, with the same amount. That's why for maximum energy recovery, you must not have both uh, external heating below the pinch and external cooling above the pinch, right? Clear? Okay, so this is the principle lah yang kita cakap tadi tu. Heat must not be transferred across the pinch. Okay, there must be no external cooling, no external cooling no external cooling above the pinch and no external heating below the pinch. Set macam mana nak buat pen ya? Right. Laser pointer je, pen tak boleh. Okay. So violation of any of the above rules will result in higher energy requirement than the minimum requirement theoretically possible. So you cannot achieve the value of QC min and QH min that you calculate in your problem table algorithm and your composite curve. Okay. Right, this is just a summary. Pinch divide the process into heat sink and heat source, and then if minimum hot and cold utility to be achieved in design, the value of Q H min and Q C min that you calculate in problem table algorithm and composite curve. Okay, okay, no heat transfer across the pinch to get the minimum hot uh, or to get the QH min and QC min. Okay, no heat across the pinch between process to process from hot to cold stream, and then there must be no inappropriate use of utilities. What does this mean? What does it means by inappropriate use of utilities? You must not have the external cooling above the pinch, and you must have no external heating uh, above the pinch. Right? This one. Okay. This statement. Right? Okay. Now, if you look here at this diagram or at this figure, this is a conventional flow sheet of a certain process, right? You have two reactor here, but then can you see where is the pinch here? Cannot, right? So basically, we can use the grid diagram to to display the pinch lah, so that we can know by just looking at the grid diagram. Okay, pinch. Okay, below this is the pinch, but pinch is hard to see. So the pinch is more clearly shown on the grid diagram, which only shows heat transfer operation. So what is the grid diagram? Okay, this is a typical grid diagram. You have hot streams, okay, and then followed by cold stream kat bawah ni. Apa laser sampai 2 ni? Right? You have cold stream and hot stream, and then what is this? Macam dumbbell ni. What is this? This is your heat exchanger where it exchange the heat between two stream, from hot to cold stream. And then you also have the cooler, right, above the pinch, and heater below the pinch. Right? Okay, this is a typical grid diagram, but utilities can also be represented as hot or cold stream. For example, you don't want to put a heater and cooler here. You can just add another stream for cooler and heater, right? And then you just place the heat exchanger lah to indicate this is the what? This is the heater that exchange the heat from steam to uh, cold stream number 2. Cold stream number 2. This is a heater. So exchange. Sorry, this is MP steam change with cold 2. So this is the one lah, right? Sorry, cold 2. Heater lah, this one heater, okay? And then cooler exchange the heat from cooling water to hot stream number 2. This one, okay? So both can be used lah, alright? Okay, this is the rule for construction. Okay, hot stream run left to the right. Cold stream run right to the left. Hot stream on the top and cold stream on the bottom. And then this is to indicate the hot utility, and cold utility is indicated by C symbol. And then heat exchanger is indicated by this dumbbell, right? Okay, now where is the pinch? Just now I mentioned that by using a grid diagram, we can see the pinch. So now where is the pinch? Okay, pinch is easily shown here. So we just indicate on the grid diagram lah. So we know that this is T hot pinch. This is T cold pinch lah. And looking at this, you know that the value of delta T min is 10, right? Okay, the implication of the pinch are easily assessed by using this diagram. You know that, okay, by this heat exchanger network, you know that nothing's wrong with this. It is allowable. But what if you have something like this? You know that there is a heat transfer from process 1 to process 2, which across the pinch temperature, which is forbidden in order to achieve the maximum energy recovery. So by using grid diagram, you can easily know lah. Okay, this is allowed and this is forbidden. This is a conventional heat exchanger network flow sheet where you have your hot stream and then your cold stream vertically lah. Okay. Okay, in conventional flow sheet, heat exchanger network flow sheet, if you change the position of heat exchanger number 3, E3, and E4, meaning that you want to place E3 here and E4 here, okay, you must reroute the process stream. Okay, but in grid diagram, if you want to change the position, just change it on the grid diagram itself without the need to reroute the string. So that's the advantage of a grid diagram, right? Okay, now heat exchanger network design for maximum energy recovery, right? Okay, these are the rules. No exchanger has a temperature difference. Uh, has a temperature difference less than delta T min. Okay, silap ni. Tak boleh dah, tak apalah. Right, so the rules is no exchanger has a temperature difference less than delta T min. Okay, previously in last week we already learned this. Okay, no process to process heat transfer across the pinch. Yang tadi ni, this one, no heat transfer between process to process across the pinch. Okay, and no heat transfer across pinch by inappropriate use of utilities. Just now yang tadi tu, no, above the pinch you cannot put external cooling, and then below the pinch there is no additional external cooler, external heater lah, heating utility. Okay, so that's the rules in order to design the maximum, the heat exchanger network with maximum energy recovery. Right, for example, you have these 4 streams, 2 hot stream and 2 cold streams with QH min equal to this and QH min. Ada pun. Nampak tak ni? Nampak tak?
Nampak, Doktor.
Alright. Ada pun. Okay. So you have these 2 hot stream and cold stream with QH min equal to this and QC min equal to this. And then you, okay, from the composite curve, okay, you also can, this value is from composite curve lah, right? This is from composite curve, or you can also get the value from problem table algorithm lah, right? Okay, using T min, delta T min equal to 10 degrees C. Now design the heat exchanger network. Okay, the first step is to divide at the pinch so that you get two group lah. One is area below the pinch, and then another one is area above the pinch. So this one is, this side is the area below the pinch, and then this is above the pinch, because this is TH pinch, this is T cold pinch. Right, so above the pinch is temperature above T equal to 150 for hot stream, and then above the pinch for cold stream is this area where the temperature is above the T cold pinch, right? So the first step is to divide, right? And then how you draw the heat exchanger network is by starting from the area near the pinch. So starting from here to this side and starting from pinch to this side lah. That's how you place your heat exchanger. Right now. But before that, you need to mesh. You need to follow these rules lah. For example, here above the pinch, okay, your CPH value must be less than CPC value. Okay, why? Okay, because, okay, this is your CP value, right? This is above the pinch. Okay, for example, if your CPH value is greater than CPH, so this is CPH value, okay, greater than CPC, okay, CP of your cold stream. So you have this pairing between hot and cold stream, and this is the apa the TH diagram lah to indicate the CP value. So this is CP with 25, and then this is CP equal to 20. Okay, looking at this, okay, as if you if you if you design your heat exchanger with CPH greater than CPC, okay, you can see that as you move away from the pinch, so this is the pinch, okay, as you move away from the pinch, it will reduce the T min here, your T min. So this T min is reduced from the value of your T min. So meaning that this is infeasible because according to the rules here, okay, no heat exchanger has a temperature difference lesser than delta T min. So the first, so you cannot design the heat exchanger if CPH greater than CPC above the pinch lah. So you must follow this. So above the pinch, you must design your heat exchanger in such a way that your CPH must be less than CPC. So if you look at the TH diagram, so as you move, okay, this is pinch, okay, as you move away from pinch, okay, you can see that you have an increase in your delta, the value of delta T min, meaning that it is feasible lah. So above the pinch, your CPH must be lower than CPC. But for below the pinch, okay, your CPH must be greater than CPC. So similarly here, if CPH is lesser than CPC, so this is your pinch because this is below the pinch, right? So this is your pinch. Okay, so below the pinch, okay, below the pinch, right? Uh, as you move, okay, away from the pinch, okay, your delta T min here reduce lah. Your delta T here is less than delta T min, meaning that the design is not is infeasible. Okay, so below the pinch, your CP, the value of CPH must be greater than CPC. So if looking at the value here, CPH must be greater than CPC, meaning that you can only design your heat exchanger by mesh or by exchanging the heat from stream 4 to stream 1 lah, because it satisfy this requirement, CPH value greater than CPC. Okay, faham tak so far? Okay, first you divide the of course the first step is to draw the hot and cold stream, and then you divide the pinch above and below the pinch, right? And then what's next? Okay, you need to sort the CP value in the decreasing order, in the descending order. So you have your CP table here. So you must create the CP table. So by listing the value of CPH and CPC in descending order from high CP to low CP lah. Okay, just now you have this value of CP. So you create a table for CPH. So start with the higher CP, which is 25, followed by 15. And then for CPC, start with higher CPC, which is 30, and then the next is 20. Okay, so you know that, okay, for the area above the pinch, you can mesh these two streams to design a heat exchanger, meaning that the heat exchanger is placed at this stream 25. CP25 is at stream 4. Stream 4 and then exchange heat, transfer heat to stream 3 with CP of 30. Similarly here, you have this pairing 15 and 20. So 15 is stream 2 pair with CP20, which is stream 1. And then you must start your heat exchanger from here lah, from your pinch, punya ni. You must, meaning that you must start your to locate the heat exchanger from right to the left. Okay. Similarly for below the pinch here, okay, your CPH value must be greater or equal to CPC. Okay, so now this is the stream. Okay, this is the stream below the pinch. Okay, first you have this, right, and then you divide lah, separate into above the pinch and below the pinch. Okay, so this is the below at this area you only have 3 stream lah below the pinch, right? Below the pinch, you only have this stream 2, 4 and 1. 2, 4 and 1. This is the area below the pinch. Okay, right? Now you have this value and then you need to sort it in descending orders. Okay, for CPH 25 and followed by 15, and then CPC you only have one stream, so put 20. So you know that you can pair between these two streams. 25 is stream 4 and then 20 is stream 1. So you place your heat exchanger here. Again, you must start at the area near to the pinch. So this is your pinch. You start from left to the right lah, right? Okay. Okay, now we have identified the feasible mesh. Okay, the question is, how big should we make them? You have your heat exchanger, but then you don't know what's the duty of your heat exchanger, right? Okay, you can do this by maximize load to tick off string to keep capital cost to a minimum. Okay, how? Okay, you can make the individual units of heat exchanger as large as possible. That is the smaller of 2 heat duties on the stream being meshed. Okay, now you have your design here. Okay. Next, you need to first calculate the value of delta H. How to calculate the value of delta H? Delta H equal CP delta T. So what is the CP value here? 15, and then delta H, delta T is 250 minus 150, which is 100. So 100 times 15, you get 1,500. And then similarly for stream 4, 200 minus 150 times CP, you get this value, and then calculate it for all the stream. Okay, now you select or you take the smallest value of heat duties. So which are the small value of the heat duties of delta H? 800 and 1,250, right? So now you take this, and then so you know that for this pairing, the duty is 1 to 5, 50 kilowatt. While for this stream, so the pairing of this heat exchanger has a duty of 800. So knowing this heat duty, you can directly calculate what is the temperature here. How? Using this value as well, this equation as well. So how to get the 203.3 here? You know that uh, your delta H here is 800, okay? Equivalent to Cp equal to 15 times delta T. So time delta T, meaning that X minus 150, right? So you get, can you calculate this? You get 800 divided by 15 plus 150. So you get 203.3. That's how you get the value of the temperature here. And then, okay, this one, no need to calculate, okay. This temperature, how to get? Using the same equation. So you know that the heat load here is 1250 equivalent to Cp 30, okay. And this one, X minus 150, right? 125 minus 30 plus 140, right? Jap. 1250 divided by 30, okay, plus 140. Betul lah. So you get 181.7 degrees C. So you get this temperature here. Okay, now looking at this value of delta H, okay, for stream 2, you only have 800, right? 800. So meaning that you need additional 700 kilowatt so that the heating requirement can be completed here. Meaning that 1,500 minus 800. So you need additional duty here. So you just add the heat exchanger, but then you don't know uh, where's to pair lah. Which stream can be paired with stream 2, right? Okay, now we calculate for this stream already. Done. And okay, this stream, the total heat load is 2,700, okay, minus 1250, okay. Right, this one just now 700, okay, because this stream also doesn't reach the total, so you just pair with this stream lah. So this is 700 kilowatt. Right. Now you total up 700 plus 125. You get only 1950. But then all the stream already fulfill the delta H value. So just add the heater lah here. Add the heater and then subtract with the total heat. So 2,700 minus 700 minus 1250, you get 750 kilowatts. Right. And if you check back, the minimum QH min or minimum heating utility required, which is what? Is 750 kilowatt, which is similar lah. meaning that your design achieve the minimum hot utility required from the ataupun you achieve the theoretical QH min lah that you calculate from composite curve or table problem table algorithm. Okay. Okay. Next, done with this. This is the area above the pinch. Kan? Now you proceed with below the pinch. You design heat exchanger below the pinch. Similarly, using the same step, you list down the value of CPH and CP cold in the descending order. So you have this value. So you know that for CP hot, you start with 25 followed by 15. And then for CP cold, you only have 20 lah. So you know that you can pair between this stream 25 and 20. So 25 is stream 4. You pair with stream 1 with CP equal to 20. Right, and then next you calculate delta H value and then find the lowest delta H value. In this case is here lah because this one tak ada pairing kot yang this one. This one tak ada pairing, yang only have pairing yang ni. So this is the lowest. So you tick. So you know that this is 175 kilowatt. Okay. And then pairing with stream 1, the same with the same duty. And then okay, because the requirement is 2,400, right? So you subtract lah 2,400 minus 1,750. So you need additional 650 kilowatt more. But what? Okay, tu kan ni. Apa? What is the external utilities? External heating utilities, heater, QH min. QH min is, sorry, QC min is 1,000 kilowatt. 1,000 kilowatt. Tu 400. Tu kan ni? 1,000 kilowatt. Ya, betul lah. Okay, so you need additional this one subtract with this, you get 600, you need additional 650. So you pair, yang ni stream ni dah okay, lengkap. You pair with this stream. Right. So you pair with this stream with the same load lah, 600 kilowatt. Right. So you need additional 1,000 kilowatt lah. So you just add the cooler, right? The cooler, because this stream, this is hot stream, require cooler lah. So cooler with 1,000 kilowatt. So that's how we design the heat exchanger network. But then if you look at this pairing, okay, or this or at this mesh, okay, it violates the CP rule. Because why? Your CPH is lower than CPC for ni lah at the area below the pinch. But then it's okay because the CP rules only apply for heat exchanger that is near to pinch. Yang the rest ni is okay not to follow the CP rule as long as delta T min is satisfied lah. So if you look at this, you calculate lah delta T and then delta T min here berapa kat sini? 150 minus 52.5, so it's greater than delta T min lah, which is 10. So as long as it satisfy the delta T min, then it's okay lah not to follow CP rules. For the heat exchanger that is far away from pinch lah, but for the first heat exchanger, of course, you need to obey the CP rules. Okay. And then once you have done, you can combine the area above and below the pinch and get the complete design of heat exchanger network. Any question? Any question? Faham tak? So you just need to do it step by step lah. So summarizing the step here. Okay, first divide at pinch off. First, obviously you need to what? To plot the ataupun to draw the stream lah. Draw the streams. Cold. Sorry. Begin with hot and then followed by cold stream. And then only you divide at pinch. So you divide the area above and below the pinch, and then you start at the pinch, meaning that you start placing the heat exchanger from the area near the pinch, and then move away from the pinch. And then you need to satisfy the CP rules here for above the pinch and below the pinch. And then draw the CP tables so that it's easier for you lah to follow these CP rules, and then so that it's easier to identify the pairing or mesh. And then use the tick off heuristic. Just now you select the lowest delta H, and by selecting the lowest delta H just now, you can actually maximize the load, which means that you can minimize the capital cost, because we design our heat exchanger as large as possible. And then fill the rest, meaning that you need to add additional heat exchanger if the duty is not fulfilled by the current heat exchanger pairing lah. And then, or you can also locate the appropriate utilities. But then you need to also follow the rule just now. No what? No external cooler at area above the pinch, and then no external heating utility at the area below the pinch. Okay. So basically you just need to follow the rules, and then you can design your heat exchanger and get the maximum energy recovery and achieve the minimum minimum external utilities. Okay. Minimum QH and minimum QC tu. Any question? Sekarang pukul apa? Almost 2. Right, so you need to do or to try this exercise, okay? And then submit lah for your attendance today. Okay. But in exam, maybe you need to this one already, the composite curve is already provided, but then maybe in exam you need to find what is QCH, QC min and QH min first, and then only you design the heat exchanger network. Okay. So that's all that I bagi attendance punya link.
Madam,
Yes.
Madam nak tanya Madam. Untuk test 1,
Test 1 tak masuk part I. Test 1
termasuk
test 1 yang from Mr. Faik.
usaha saya je.
Ya.
Okay.
Sekejap. Attendance. 22. Okay. Right. Boleh faham tak? I yang ni memang nak exam rasanya final exam dengan test pun ada. Copy. So make sure each and every one of you are able to draw to design the heat exchanger network that can maximize the energy recovery. And of course, make sure you able to to extract the QH mean and QC mean from problem table algorithm and composite curve. Okay. Right. So that's all for today. We continue tomorrow. Thank you and Assalamualaikum.
Betul.
Okay.
Thank you, Doktor.
Yeah, thank you. Welcome.